This is a very basic flute. So in practice, it's a pipe which contains an air column. So when I blow over this, over the mouth of this, I create a tone. So what happens here when I blow over here is that we have a vortex shedding in this region here. And this vortex, turbulent vortex shedding, creates sound pressure disturbances or pressure disturbances here. And they propagate as plain one-dimensional waves along the air column down to this end where they reflect. This turbulent vortex shedding contains a very, very wide band of frequencies, and some of these frequencies are amplified by resonant conditioning determined by the length of this pipe. So if I use a shorter pipe, then I get a different tone frequency. So this, I guess, thousands of years ago, created the first ideas to how to create an instrument like this, a flute, where you can blow in this, and the labia here creates this vortex shedding, turbulent vortex shedding, and then by putting your fingers over the holes here, you change the length of the resonant air column here in order to create different tones. Well, I'm not the best flutist, as you can see, but that is the basic idea of the flute. We are going to derive the linear acoustic wave equation. For this reason, we need some assumption that simplifies this derivation. And the first assumption is that we have a homogeneous medium. And that means that the medium's properties is independent of position. For instance, the speed of sound does not depend on where we place ourselves. We also assume that the medium is isotropic, and that means that the properties is independent on the direction we look into. So the X, Y, and Z directions, for instance, are equivalent. We have an adiabatic process, a thermodynamically speaking, adiabatic process. And that means that we can neglect any heat conduction between the low and high pressure regions when the acoustic wave is propagating through the medium. So no heat conduction. The opposite is an isothermic process where the heat conduction makes the temperature homogeneous in the medium. But in this case, we assume an adiabatic process, and that has been shown to be a very, very good assumption for air in normal conditions, normal temperature and normal pressure. Finally, in order to be able to linearize the equations, we assume small amplitudes. So let's start with the first of three basic equations, and that is actually Newton's second law. The force is equal to mass times acceleration. And what we're looking at here is a cubic, small element of the medium. The size is delta x, delta y, and delta z. And when the sound propagates through the medium, it will act, let's assume now that the propagation direction is the x direction. On the incoming side of the cube or box, element box, we have a force, which is equal to the sound pressure times the surface of the side, delta y times delta z. And on the other side, we have an opposite directed force equal to the pressure on this side times the surface. So Newton's second law then says that the mass equals the acceleration is equal to the net force. So in our case, we have, well, rho zero here is the ambient density of the medium. So if you multiply the density with the volume of the element, then you get the element mass, of course. And then this dux dt is the acceleration of the particle of the fluid element. So ux here is the velocity, element or particle velocity in the x direction. And on the right-hand side, we have the resultant force in the x direction. And as you can see, we can, if we sort of rewrite this term, we can write this as a pressure difference times the area delta y delta z. So using this then, if we divide this equation here, Newton's second law, with the element volume, and then we let the in the limit the side length delta x go to 0, then we actually can rewrite this as this to this form. So in the right-hand side now, we have the partial derivative of the sound pressure in partial derivative with respect to the x-coordinate. And the minus sign here, of course, depends on this side there, that we have this definition here of the partial derivative. So next one of the three basic equations here is the known as the acoustic mass continuity equation. So in words, the mass continuity equation says that the mass passing into the medium element here minus the mass going out of, passing out from the element must be equal to the mass change in the element. And that is what we are going to study now. So this expression here, the density times the particle velocity times the area, the surface area here. Actually, the particle velocity times the surface area is equal to the mass flow into the the mass that passes this area delta y delta z. Or sorry, the volume that passes this area. And when we multiply it with the density, then of course we get the mass that passes the area. If we do the same thing on the other side, then we get the mass flow out from the element. And the difference between these two now is, of course, the change per time unit of mass of this medium element. So delta m, if we denote the mass change with this, can be expressed in this manner. So exactly like before now, if we divide both the left-hand side and the right-hand side of this equation with the volume of the cube, of the medium element, then we see that, and also if we divide with the delta t, the time increment here, then we see that we on the left-hand side get the time derivative on the mass, and on the right-hand side we will get the density times the partial x derivative of the particle velocity in the x direction. So this is what we obtain. This is the one-dimensional acoustic mass continuity equation, well, and one-dimensional. In this case, it's the x direction that we're looking at. The third of these three basic equations is the thermodynamic law. And for a gas, like air, we use the ideal gas law, which can be stated in this manner, as you may know from your physics courses. And R here is the ideal gas constant, T is the temperature, and M, capital M here, is the molar mass of the medium. P is, of course, pressure, and ρ is density. And index 0 indicates ambient conditions. So P here is the sound pressure, and ρ is the disturbance of the density caused by the propagating sound wave. So if we should not go into details here, but it turns out that if we assume small perturbation and an adiabatic process, then we can reformulate this in the following form. So the sound pressure now is equal to a constant beta, a medium-dependent constant beta, times the ratio of the density perturbation over the ambient density. And this beta is also known as the adiabatic compression modulus, and that is totally equivalent to the elasticity modulus in solid mechanics. So for gases, beta, this adiabatic compression modulus, is equivalent to the modulus of elasticity. So if you use these three basic equations and combine them, then we can derive this one-dimensional linear acoustic wave equation. And in this case, since we have treated the x direction, we will get this equation. So this equation is the acoustic wave equation. And it describes a plane wave propagating in the x direction. So this is an animation. So let's assume now that this duct here, or pipe, with this oscillating piston here, is directed in the x direction. And then you can see here the density, all these dots here should represent an air particle. And you can see you have compression areas here with high density, and you have rarifications here. And as you can see here, these wave fronts are plane, and they propagate with a certain velocity here, which turns out to be the sound speed. And you can also see, if you focus on one particular point here, you can see that they oscillate back and forth around the average position. And the oscillation speed, that's the particle velocity. So remember now that the speed of sound, c, is something completely different than the particle velocity, u. That's very important to remember. Okay, if we now divide the wave equation we saw before with with beta, then we can rewrite it in this. You remember that beta was written here. So if you divide this equation with beta, then we can formulate it in this way. So the factor multiplying now d2p dt2 is now named 1 over c2. And here is where the speed of sound pops up. So the speed of sound, defined in this way then, is the square root of the adiabatic modulus, compression modulus, over the ambient density. So the lower the density, the higher the sound speed. And the higher the adiabatic compression modulus, the higher the sound speed. So these two parameters for a gas determines the speed of sound in the gas. Now, if we generalize this, then we can arrive at a three-dimensional version of this linear acoustic wave equations. And well, as you can see here, the only difference is that the d2p dx2 term is added with the other two coordinate directions, y and z. So this is the general three-dimensional linear acoustic wave equation. Now, well, I've chosen this flute because it shows actually a combination of where you can use a combination of the linear one-dimensional and three-dimensional wave equations. So in the first part here, this part, this flute, I mean, when you blow over this hole here, you excite waves propagating in the body of the flute here. And that is modeled with one-dimensional propagation, as one-dimensional propagation. And then when the sound is radiated to the listener, then we have three-dimensional propagation. So some more applications. If you have sound propagation in pipes, you can have exhaust systems, ventilation pipes, fluid machinery. In this case, it's an engine. So in these two parts here, the incoming and outcoming part here, pipes here, you can model the sound propagation with the one-dimensional acoustic wave equation. Outdoor sound propagation is a typical example of where you use the three-dimensional case. And this is an alarm. So if you want to describe now how this sound propagates from the source here to a listener here, then you use the three-dimensional version of the linear acoustic wave equation. So that's all for now.